Welcome to the deep dive. Today, we're not just looking at physics. We're staring straight into the beautiful, unified heart of the universe. We are tackling Chapter 26 of Volume 2 of the Feynman Lectures on Physics and its mission to explain one of the most elegant concepts in electrodynamics, the Lorentz transformations of the fields.
This is a fundamental turning point, really.
Yeah.
For centuries, we treated electricity, math BFE and magnetism, math BFEters, as two separate forces. Maybe related, sure, but distinct. This chapter just rips that idea apart. It shows us they are inseparable. Change your speed relative to a charge, and what you measured as maybe a pure electric field instantly transforms. It becomes a mix of electric and magnetic fields. They're merely two perspectives, you see. Two sides of the same relativistic electromagnetic coin.
That's the core thesis, then. We're going to walk through the logic of this unification, starting with the sources of the field, the potentials, and ending up with that grand, compact equation of motion. We're really aiming for conceptual clarity here, trying to give you that aha moment of how these fields behave when relative velocity, well, dictates reality.
Okay, so to start, we really must describe the source of the fields properly. Let's imagine a charge q moving at a constant velocity v. Now, when dealing with moving charges, we can't just use the classical scalar potential. Doesn't work quite, right? We have to use the four potential. This bundles the scalar potential together with the vector potential.
Okay, hold on. Why is that necessary? Why do we have to combine them into a single four vector like that?
Well, it's because in relativity, space and time aren't separate. They're unified into space-time, right? So any physical concept that changes under a Lorentz boost, which both all math BFA definitely do, it has to be represented by a four vector. This ensures the laws of physics look the same for all observers, no matter how they're moving. The four potential is basically the required relativistic tool for describing the field source.
Right, okay. And as soon as we deal with fields propagating from something that's moving, we hit that time delay problem. We can't ignore it. You called it retarded time.
Precisely. Yeah, retarded time is crucial. So we measure the fields at our position, x, y, z, at some time t, but those fields we feel now, they aren't generated by the charge's current position. No way. They are actually generated by the charge's position and velocity at an earlier time, 4 times. And that time difference, $3t, is exactly the time it takes for the electromagnetic signal traveling at the speed of light, to get from the charge to us.
So if you see a charge, say Q, zip right past you, the electric field you're feeling right now isn't determined by where it is now, but by where it was a moment ago.
Exactly. And the mathematical solutions for the potentials, they confirm this completely. The value of $Hg at a math PFE right here, right now, depends only on the position and velocity of the charge at that sort of historical retarded time. It's like the universe itself is confirming that electrodynamics is inherently relativistic even before we explicitly start talking about Lorentz transformations.
Okay. So we have the potentials derived using this retarded time concept. Now what?
Now, we take those potentials, Hg time and math BFE, and we perform the necessary calculations, the standard differential operations, gradient, curl, time derivative, math BFE partial T enable times math BFE. This gives us the actual measurable fields, math BFE and math BFE, created by this constantly moving point charge.
Let's try to visualize this. If the charge were just sitting still, its electric field lines would be perfectly radial, right? Like spokes on a wheel going out equally in all directions. That's just the basic Coulomb field. What happens to those nice, neat field lines when the charge starts moving, maybe really fast, near the speed of light?
Oh, they distort dramatically. Visually, it's quite striking. The electric field lines are no longer uniform. Now, along the actual line of motion, they stay radial, but perpendicular to the motion, they get intensely compressed, squeezed inward toward the plane that's perpendicular to the velocity vector.
Ah, that squeezing effect. That sounds like the key visual takeaway here. And the source mentions the field strength itself changes too.
It does. The total electric field strength, E, gets amplified. It's boosted by that very familiar relativistic factor, $1C for OV on V C22, the gamma factor.
And this distortion, this squeezing, it's not just some mathematical artifact, is it?
No, not at all. It's the physical manifestation of Lorentz contraction. Remember how moving objects appear shorter, contracted in their direction of motion? Well, the electric field itself reflects this geometric contraction. The charge effectively looks contracted in the direction of dollars, and so its field lines appear powerfully focused or squashed inward in that transverse direction. It's a really perfect visual link between electromagnetism and special relativity. Quite elegant.
Okay, so motion distorts the E field. But it does more than that, right? It actually creates the B field.
Exactly. And the source material gives us this wonderfully simple connection, at least for a charge moving at constant velocity. The magnetic field math BFB turns out to be directly proportional to the cross product of the velocity vector math BFV and the electric field math BFE, scaled by 2 Tauler's 2.
The relationship is math BFE times math BFE ZFE2.
That specific relationship is maybe the first profound clue we get towards unification. It basically says, wherever you have an E field in relative motion between the source and the observer, you must also have a B field. It's not optional. And importantly, for slow speeds, much less than $t, that velocity term approaches zero. So the B field vanishes, and the E field just snaps right back to the standard Coulomb law. That's our necessary consistency check with classical physics. It all fits together seamlessly.
Right, it contains both classical and relativistic physics in one formula. That's neat. Okay, so we've established that motion generates and distorts these fields. Now let's get to the heart of the chapter. How do these fields look to us if we are the ones moving? If we shift from a stationary frame, let's call it Zillers, to a frame Zills we measure, to a frame C Thelars that's moving relative to Thelars, the fields we measure, math BFEOR and math BFBO, they have to transform correctly according to relativity.
Yes, and this is where the old way of thinking breaks down. If we just treated math BFE and math BFB as two completely separate three vectors, like classical physics might tempt us to do, and then try to apply a simple Lorentz boost to each one independently, it would give total nonsense. It just wouldn't match experiments. That's because as we move, components of the E field start, showing up as B field components in our frame and vice versa. They mix together. So we need a structure, a mathematical object that handles all 6 field components x as bx by bzz at the same time. And it has to ensure they transform together as one unified entity under a Lorentz transformation.
And this is where we finally meet the star of the show, right? The field tensor. This is the required mathematical packaging that solves the whole problem.
Exactly. The field tensor is the hero here. It's technically a second-ranked tensor in 4-dimensional spacetime. You can think of it as a $4 times 4-4 array or matrix. And it neatly contains all 6 independent components of the electromagnetic field. It's also famously antisymmetric. That means we fact, sim u.
Antisymmetric. That's important, isn't it? Because F11 or FET22 must be 0 then, and F12 is just the negative of FET21.
Precisely. That antisymmetry is key. It forces the diagonal elements, F11, etc., to be 0. And it means that pairs like F12 and 21 aren't independent. One determines the other. That's how this $4 times 4-4 structure, which looks like it should have 16 components, actually only holds 6 unique independent pieces of information.
Which are?
The 3 components of math BFE and the 3 components of math BFB, they all fit perfectly.
How do they fit? Where do E and B components sit in this tensor?
If you look at the structure, the components with purely spatial indices, like F12's 21 twic, those contain the magnetic field components, B's B, roughly speaking, depends a bit on convention. And the indices that involve the time component, index 0, like 51053, those contain the electric field components, XES. So by merging all 6 components into this single geometric object, the tensor provides the correct mathematical framework for how the fields must transform under a Lorentz boost. The whole transformation process gets summarized by a single elegant matrix multiplication rule involving this tensor.
Okay, that's the machinery. Let's get to the result of that transformation. Feynman distills the complex tensor math down into simplified transformation rules for the math BFEP and math BFE vectors themselves. What are the crucial rules we need to remember from that?
Right, the practical outcome. The rules are actually quite insightful and split based on direction relative to the motion. Let's say we are moving along the scale galaxies with velocity math BFE. Yeah. The components of math BFE and math BFD that are parallel to this motion, they're completely unchanged. So UXE equals X and BFE equals BX's. Easy enough.
Okay, parallel components stay the same, but the components perpendicular to the motion, that's where the action is, where the mixing happens. This seems like the core conceptual shift.
It absolutely is. So imagine you have a purely static electric field pointing, say, only in the lab tray and the lab frame. No dollar field at all. Now, you observe this field from your moving frame. What do you find? You find that the original IR has transformed. It's not just a new electric field component, Cagliari scaled by gamma. No, it has also generated a new magnetic field component. The transformation equations explicitly show this mixing, EFEBI and DELEVI2, and BOLIVBEIC. If ELAS was 0 initially, you still get a BV from EF.
So the mixing is mandatory. It has to happen.
It has to. Think about the classic example Feynman uses, a parallel plate capacitor. Sitting still in your lab, it creates a pure static math BFE field between the plates. 0 B field. Simple.
Okay, standard setup. Now imagine you are an observer zooming past that lab at high speed. What do you see?
Well, from your perspective, you are stationary, and the capacitor plates are moving backward. And the stationary charge is sitting on those plates in the lab frame. To you, they now appear as two sheets of moving charge. One positive current sheet, one negative current sheet, moving in opposite directions. And what do currents create?
Magnetic fields.
Exactly. So according to your frame of reference, there must be a magnetic field present that wasn't there in the lab frame. The pure E field measured in the lab frame must transform into a mixture of both EI and bidollars in your moving frame, just to ensure the laws of physics are consistent. It's not like the field physically changed out there. It's that your perspective, your state of motion, changed the fundamental division between what you label electric and what you label magnetic.
That really drives it home. It's about perspective.
Okay, moving to the final section, section 4. How do we connect these transformed fields back to the actual physics of motion, back to the force they exert on a charged particle?
Right, we need the relativistic force law. We start with the familiar Lorentz force equation, virus, math BFE plus math BFE times math B, but now everything in it needs to be interpreted relativistically. The velocity math BFE is the particle's velocity, and critically, the momentum associated with this force isn't math BFE, it's the relativistic momentum PE phi equal amp BFE square phi.
And to make the force law properly frame independent, consistent across all inertial frames, we can't just use the classical three-component force vector math BFE. We need to upgrade it. So we introduce the 4 force and the particle's 4 velocity. What's special about the 4 force? The 4 force solvers is crucial. It's a 4 vector, so it behaves correctly under Lorentz transformations. Its first 3 components are related to the standard force components times gamma, but the 4th component, a time component, is related to the rate at which energy is being transferred to the particle. Power, essentially. It packages force and power together relativistically.
Okay, 4 force, 4 velocity. What else is needed for the equation of motion?
And here is maybe the most subtle, but absolutely the most crucial step in writing the fully relativistic equation of motion. The rate of change of momentum. We can't take it with respect to ordinary coordinate time t. That time is relative. Different observers measure different intervals. We must take the derivative with respect to proper time.
Proper time. Why is proper time the chosen clock for relativity?
Because proper time is the Lorentz invariant. It's a scalar. It's the time interval measured by a clock that's actually moving with the particle itself, the time elapsed in the particle's on rest frame. Every observer, no matter how fast they're moving relative to the particle, will agree on the value of a proper time interval, dot-tau. It's universal. Using dot-tau in the denominator ensures that the equation of motion, the physical law, holds true for all inertial observers. It's the invariant anchor that makes the whole relativistic framework consistent.
So you put all these pieces together, the 4 force MAMO, the 4 velocity 1 mu, the particle's invariant rest mass, time no, the unified field tensor, and differentiation with respect to proper time tau.
And you arrive at this single, stunningly elegant equation that summarizes the relativistic dynamics of a charged particle interacting with an electromagnetic field.
Now frac d2x mu qu.
Wow.
Oh.
Let's unpack that slightly. 22x2 is essentially the rate of change of 4 momentum with respect to proper time. Exactly. It's the relativistic generalization of Newton's second law, or F putty PdDT, and it states that this rate of change of 4 momentum equals the 4 force, which in turn is given by the charge times the contraction of the particle's 4 velocity with the field tensor. It beautifully connects the particle's motion to the unified field through its charge, all expressed in a form that remains true regardless of the observer's inertial frame. It's the ultimate synthesis.
What a journey indeed. We started with just a simple moving charge, calculated its potentials using retarded time,
Derived its distorted E field and the necessary accompanying B field.
then realized these fields must transform into each other when we change our frame of reference, leading us to the field tensor.
And finally, express the force exerted by this unified field on a charge using 4 vectors in proper time, resulting in that one compact, universally valid equation of motion.
It really proves that electricity and magnetism aren't separate forces. They're inextricably linked aspects of a single entity.
That's the fundamental truth. The Lorentz transformation rules, derived ultimately from the 4 potential and the structure of spacetime, show us precisely how much of one field appears to be converted into the other based purely on relative velocity. The necessity of special relativity forces us, really, to abandon the idea of separate math BFE and math BFE fields. They're just different manifestations, different slices of the same underlying electromagnetic field, perfectly captured by that six-component field tensor band.
Okay, here's a final thought for you, the listener, to ponder, building on this deep dive. We saw that if you move relative to a static E field, you must observe a B field. Now think about the energy. A static E field has potential energy stored in it. A B field also stores energy. If you observe a purely static charge distribution, but from a frame moving at nearly the speed of light, $2, you'll see an incredibly strong magnetic field appear due to the Lorentz transformation. Where does the energy associated with this new magnetic field come from? How does the transformation handle the conservation of the total electromagnetic energy momentum of the system across different inertial frames? Something to mull over.
Indeed. It forces us to appreciate that energy and momentum themselves transform as part of the four-momentum vector, ensuring conservation holds relativistically. It's all connected.
Thank you for joining us for this deep dive into the relativistic heart of electrodynamics, guided by Feynman's insights in Chapter 26. We hope this has provided some clarity and maybe boosted your confidence for your own studies.